So now that we've gotten comfortable with vectors, we're going to use these vectors to expand our view of how we can take derivatives and what direction we can take derivatives in. So this is going to expand our knowledge from partial derivatives we've looked at before to directional derivatives. So let's go ahead and introduce a little bit of new notation to start with. Suppose I have a function z equals f of xy, so a function of two variables. And let's say we have a vector v, which is ai plus bj. So it goes a units in the I direction, b units in the j direction. Then for shorthand here, we'll write f of v for f of ab. So notice you're just taking the I component and plugging it in for x, and the j component for plugging it in for b, or for y. But this shortens the notation a bit, and this will be nice with some of the stuff we've got coming up here to shorten our notation a little. So for an example, if I look at f of v plus h times j, this is just f of a comma b plus h. So let's think of our partial derivatives that we've seen before. So if we're looking at the partial derivative at some point ab, we can create that vector v, ai plus bj, and then notice we can rewrite our partial derivatives here. So remember, when we're doing the partial derivative with respect to x, we only want to change in the x direction, so that's only in the I direction. So we can rewrite this as the limit as h goes to 0 of f of v plus hi minus f of v over h. So notice that first term, if we expand out in our notation, that would be f of a plus h comma b, and then it'd be minus f of a comma b, which is exactly how we define the partial derivative with respect to x. And then the same thing for the partial derivative with respect to y, only now we're changing the y direction, so we add hj instead of hi here. So if we want to view this in terms of a graph here, notice in this case where the orange curve here is when we fixed a particular value of x. In this case, it's fixing x is equal to 2. And so we go out to this point, which in this case is the point 2 comma 2, and then f of 2 comma 2. And notice when we ask for the partial derivative, we're asking how is this function changing when we move in the j direction here. So when we change the y value. So in this case, we're thinking of our directions now as given by vectors. So when we do that setup, it makes it pretty clear there's nothing really special about going in the I or the j direction. We could do that without vectors because we were changing only the x or the y. But now it seems more natural that we should be able to change vectors in any direction, not just the I or the j direction. So if we let u be any unit vector, so we'll take u to be u1i plus u2j, and it is important that this is a unit vector. We define the derivative of f in the direction of u, and now our notation here is that f with a little subscript u, and notice here u is a vector, so when I'm doing this on typing, I make a boldface u, but if we're writing this out on the board, we'll see since u is a unit vector, it'll be f with a subscript u hat here. And we want this at the point AB, so v is still the vector ai plus bj. Then this is the limit as h goes to 0 of f of v plus hu minus f of v over h. And if we go ahead and write this out without the new notation, notice this is f of a plus hu comma b plus hu minus f of ab over h. So now instead of just changing in the x or just changing in the y direction, we're changing in the x and y direction potentially. So let's see some pictures so we can understand what this is. We're not going to actually calculate any directional derivatives in this video. We're going to see in class how to actually calculate them. So for us, we're just trying to understand what's going on and what we're looking at right now geometrically and in terms of how the equations are generalizing the partial derivative. So one thing to note before we go on is, from what we saw before, if I want to write the partial derivative of x with our new notation, it's f with a subscript, the unit vector I, and the partial derivative with respect to y is f with a subscript of the unit vector j. So make sure you understand how those two things are equal before going on. So let's see how we can view this. So in this case, I've changed what I'm looking at here. I'm not fixing x to be some number and y to be some number. So for this particular curve, I graphed here in the orange, this is the curve on the surface where x is actually equal to y. And this unit vector is pointing in the direction of that curve. It doesn't look so much like it here. It looks like it's kind of going off to the side. But if we rotate it, we can see it is actually going exactly in the direction of that orange curve. So when we ask what is going on for the directional derivative in the direction of u, we're asking exactly how does that function change when we move in the direction of u. So now if we think about this in a real world example, you could think of you're standing on partway up a giant hill here, and what you're asking is if you look in the direction of u hat here, what does the shape of the hill look like? So in this case, you'd be looking down. So the height is going down when you look in the direction of u hat. If we change to negative u hat, you'd be looking up the hill. And sometimes this is easiest to picture using contour plots because then everything is in 2 dimensions, so you can see um, exactly the unit vectors in the xy plane. So in this case, that surface we just looked at, here's some contour plots for that. And looking at the point 2, 2, which is where we were looking at, this is the vector picture here is just the vector j hat. So this is asking how are we changing in that direction. So you could use the contours to estimate your values of f here to see how it's changing. And if we change to the vector u hat, which was in the direction of the x equals y curve, we can see that this direction vector is just going out at the 45-degree angle here. So this would be, this unit vector would be square root of 2 over 2i plus square root of 2 over 2j. And we can kind of see how this is changing here. So we're starting at the curve 2 here, and we're basically going just a little bit past the curve to -4. So we can see in this direction the height is decreasing as we saw on the previous slide. So what we'll do in class is we'll actually talk about how to calculate these directional derivatives and a little bit more about what they're useful for and what they can tell us about our functions.